Hi, everyone, and welcome to Module 6. In this lecture, we are going to discuss methods for analyzing the relationships between multiple variables. Initially, we will focus on analyzing the relationship between two continuous variables. It is common to wonder how changes in one variable may affect the other variable. For instance, we may ask how wait time affects patient satisfaction, or how changes in a patient's diet affects their long-term prognosis for some disease. From there, we will expand the discussion to include the relationship between three or more variables and between quantitative and qualitative variables. We will discuss how multiple regression can be used to predict common outcomes in medical settings. Multiple regression is one of my favorite areas of statistics, so hopefully you enjoy it too. The simplest way to determine the relationship between two variables is to examine how they change together. Does an increase in one variable correspond with an increase in a second variable? Or is the opposite relationship true? Perhaps an increase in one variable is associated with a decrease in a second variable. This type of relationship is called a linear relationship. It is called that because a perfect relationship would form a straight line on a scatter plot. We can obtain a crude measure of the linear relationship between two variables by inspecting the scatter plot. In the first scatter plot, we see the relationship between height and weight. The plot demonstrates that those who are generally taller tend to weigh more. In this second plot, we see the relationship between wait time and patient satisfaction. Here we see that as wait time increases, patient satisfaction tends to decrease. These graphs can paint a broad picture of the linear relationship between two variables, but they do not give us an exact measure of this relationship. Also note that in both scatter plots that there is not a perfect one-to-one correspondence between the two variables. That is, growing another inch does not guarantee a constant increase in weight or even guarantee an increase at all. The same is true about the relationship between patient satisfaction and wait time. A more precise way of measuring the linear relationship between two continuous variables is through the Pearson correlation coefficient, which we discussed in the first module. Recall that the Pearson correlation coefficient is a statistic that quantifies the relationship between two variables. The Pearson correlation coefficient can range from -1 to 1, with negative values indicating that as one variable increases, the other decreases, and positive values indicating that both variables increase together. The scatter plot showing the relationship between height and weight would have a positive correlation because both increase together, while the scatter plot showing the relationship between wait time and patient satisfaction would have a negative correlation because as wait time increases, patient satisfaction decreases. The strength of the relationship is given by the distance from zero. That is, correlations close to 1 or -1 indicate a very strong relationship, while a correlation close to 0 indicates no relationship between the two variables. In this slide, you see several scatter plots showing different values of the correlation. Notice that the first one is close to 0, indicating, and we don't really see the straight line we would expect in a linear relationship. The other two are closer to 1 and -1 respectively, and we do see this more of a straight line pattern. The correlation coefficient is a nice tool, but it is limited solely to explaining the strength and relationship between two variables. We are often more interested in making predictions for one variable based off the value of a second variable. For example, we may want to predict the weight of someone who stands at 6 foot 2 inches tall. Linear regression models are a versatile tool that can accomplish this task. Referring back to Module 2 when we discussed the idea of an independent and dependent variable. As a brief review, the dependent variable is affected by changes in the independent variable. We will denote the independent variable as x and the dependent variable as y. Remember, we're saying that x causes y to change, or is associated with changes in y. Further, we're going to denote each individual observation with the value I. So for instance, if we have the height and weight of one person, they're going to get a value of I is equal to 1. The second person will get a value of I is equal to 2, and so on. The linear regression method fits a line through the data that minimizes the distance between the line and the points on the scatter plot. This line is called the regression line, and you can see it in the plot on the slide. The line goes through the data and attempts to shrink those data points to get as close to the line as possible. Notice how the line goes through the middle of the data. Also notice that some values are closer to the regression line than others. This occurs because different values for y may exist for a single value of x. For example, if we are predicting someone's weight using their height, one person who is 6 foot tall may weigh 160 pounds, while another person who is also 6 foot tall may weigh 180 pounds. The regression line attempts to be as close to these two values as possible, but obviously it cannot go through both values because they're different. The linear regression formula for one independent variable predicting a dependent variable is the predicted value of y, which is the y with the caret over it, for the individual I, which is equal to beta sub 0 plus beta 1 x plus the individual error from the model. So we need to define what these terms mean. As I just stated, y hat is the predicted value of the dependent variable for an individual in your data set. Beta sub 0 is the y-intercept. This is the predicted value of the dependent variable when your independent variable is equal to 0. So using the height and weight example, this is your predicted weight when someone's height is 0 inches tall. Beta sub 1 is the slope. The slope is the change in y for a 1 unit increase in x. So this would be the change in your weight, using our example, for a 1 inch increase in height. We are typically most interested in interpreting the slope because that tells us how our dependent variable changes in relation to our independent variable. Finally, E sub I is our error term, and it tells us how far off our predictions are for an individual. This value across everyone in your sample is assumed to average out to 0, so we're going to ignore it for this module. This error term will become more important in Module 3 when we discuss some more advanced models. Now, this may seem like a lot of information, and it may be intimidating, but I promise it's not that bad. The following example should demonstrate that. Below, you will find the regression equation for predicting a person's height based off their, predicting a person's weight based off their height. We have the formula that a person's predicted weight is equal to negative 500, the y-intercept, plus 10, the slope, times x, which is the value we're going to plug in for height. So in this example, the slope is equal to 10. This means that for a 1 inch increase in height, we expect weight to increase by 10 pounds. This makes sense because we expect taller people to weigh more. We also have the y-intercept of negative 500, but it's not really useful to interpret the y-intercept. We will demonstrate this using the above example, in which the y-intercept is equal to negative 500. This value tells us that we predict that a person who is 0 inches tall will weigh negative 500 pounds. This obviously doesn't make sense for a number of reasons, the main one which is it's not realistic. A person who is 0 inches tall doesn't exist, and it's impossible to weigh negative pounds. For this reason, we really don't interpret the y-intercept. Finally, we can use this formula to make predictions about the dependent variable. To make a prediction, we simply substitute in a value for x into the regression formula. So in our example, we're going to substitute in some height into the formula. So suppose we want to predict the weight of someone who is 68 inches tall. That is, someone who's 5 foot 8 inches tall. We simply plug 68 in for x, and we get negative 500 plus our slope of 10 times the value we want to predict, 68, which gives us 180 pounds. So we predict that someone who is 5 foot 8 inches tall is going to weigh 180 pounds. As you can hopefully see, linear regression is an incredibly useful tool. However, it is not without its limitations. The first limitation of regression is that these models assume that each observation or each person in your data set is independent of one another. That's just another way of saying that everyone in our sample has been selected at random. The second limitation of the linear regression assumes that a straight line relationship exists between the independent and dependent variables. If this relationship is not true, then the linear regression model will not accurately represent the data. Finally, it is not appropriate to use linear regression models to make predictions outside the range of the independent variable. That is, let's say we have a data set of people's heights, and the tallest person is 6 foot 8 inches tall. We can make predictions up to 6 foot 8 inches, but anything above that, we cannot make a prediction about. And the reason for that is we don't know if the linear relationship in the model holds for values outside the range considered in the data. We can apply this to making predictions about events in the future. So if we're looking at predicting what happened, say, from 2000 to 2010, we have that data. But we can't make predictions about 2030 because it hasn't happened yet. We have no idea if our model will still fit for these future events that we have no data on. Once we obtain a regression model, we may ask ourselves, how well does our model predict the dependent variable? We can do this in 3 ways: by testing the significance of the slope, by determining how much variance in y is accounted for by x, and by testing the overall model fit. We will use Excel to obtain each of these pieces of information. We can conduct a hypothesis test for the slope, much like we did when we tested hypotheses about means. The null hypothesis, which if you'll recall says that nothing is going on, for the slope states that there's not a relationship between x and y. This corresponds to the slope of 0. If our slope is 0, there's no relationship between x and y. So we can write the null alternative as beta sub 1, our slope, is equal to 0. Our alternative hypothesis does say x affects y. So we're going to write that beta sub 1 is not equal to 0. This is going to be true for any regression equation we do in this module. We are going to use Excel to calculate the test statistic and p-value for the slope. As always, a p-value less than 0.05 indicates that we should reject the null hypothesis and conclude that x does predict y. The second method for assessing how well our model predicts the dependent variable is through something called the coefficient of determination, which we write as r squared. This is the proportion of change in y that is directly related to changes in x. This statistic ranges from 0 to 1, with a value of 1 indicating that all the change in y is due to x, and a value of 0 indicating that none of the change in y is due to x. That is, x does not affect y at all. The closer to 1 that r squared is, the better our model does at predicting the dependent variable. When there is only one predictor in the model, the coefficient of determination is actually equal to the squared Pearson correlation coefficient that we discussed earlier and in Module 1. The final method is to conduct a hypothesis test of overall model fit. This is identical to the F-test we learned about in the last module when conducting an ANOVA. In fact, regression and ANOVA models are identical. With only one predictor, the F-test of overall model fit is identical to conducting a hypothesis test on the slope. However, if a linear regression model contains multiple predictors, this test measures how well all the independent variables together do in predicting y. That differs from the test of the slope, which just tests whether one predictor outside of any other predictors does a good job at predicting y. So let's go over an example. We're going to evaluate whether a patient's age predicts the length of their hospital stay. We obtain the following results for Excel, and I include a document in the module about finding regression models using Excel. So there's a lot of information here. First, we can pull the regression equation from the column titled Coefficients in the third box. The value for intercept indicates that the y-intercept is 22.249 days. Or in other words, a patient who is 0 years old would have an average stay at the hospital of about 22 days. The value of age corresponds to the slope. For a 1 year increase in patient age, the length of stay increases by 0.19 days. So therefore, we can write the regression formula as the predicted length of hospital stay, y hat, is equal to our y-intercept, 22.25, plus our slope of 0.19, times any value of age we want to plug in. So, we had three ways of testing the relationship in linear regression. The first was to conduct a hypothesis test on the slope of age. So we're going to look at, is there a significant relationship between age and length of stay, or does age predict length of stay? The null and alternative hypotheses are beta 1 is equal to 0 for the null, and beta 1 is not equal to 0 for the alternative. We can obtain a t-value and a p-value from the age row in the third box. In this case, the t-value for the slope is 8.29, and the p-value is 3.61 times 10 to the negative 16, which is a very small value that is much less than 0.05. As a result, we reject the null hypothesis and conclude we have evidence that age does predict the length of hospital stay. The other hypothesis test we discussed was testing the overall model fit by using an F-test. Again, this is the same thing we did with the ANOVA, so the null hypothesis is F is equal to 0, and the alternative hypothesis is F is not equal to 0. In the ANOVA table, in the second table, we find an F value of 68.73 and a p-value of 3.61 times 10 to the negative 16. Notice that this is the exact same p-value we obtained when we tested the slope. That is because, as I said earlier, when you only have one predictor, the hypothesis test for the slope and the hypothesis test for model fit are the exact same thing. Again, because this value is much less than 0.05, we reject the null hypothesis and conclude our model does a good job of predicting hospital stay. Now, maybe we want to know of exactly how good of a job does our model do. Well, we do this by looking at the R-squared statistic, which is our coefficient of determination in the first box that says regression statistics. In this scenario, our R-squared value is 0.0644. This indicates that 6.44% of the change in hospital stay is due to changes in age. So age accounts for 6.44% of the predictability of hospital stays. So while age is a statistically significant predictor, it doesn't really account for much of the length of hospital stay. So far, we've discussed making predictions using a quantitative predictor. We've used the quantitative variable height to predict weight. We've used a quantitative variable age to predict length of stay. As I said earlier, regression is a very versatile tool, and that means we can use qualitative predictors in regression models as well. This is done through a process called dummy coding. When dummy coding, one variable of the qualitative predictor is designated as a reference group, and every other level of the predictor is compared against that reference group. A dichotomous indicator, which means the variable takes on values of 0 or 1, is used to identify which level of the variable is being compared to the reference group. The slope, then, is the mean difference between the reference group and every other level of the qualitative variable. So let's go over an example to see how this works. Suppose we wanted to predict a person's life expectancy based off the country they were born, and we only have 3 countries in our data set: the US, France, and Japan. We could choose any of these 3 countries as a reference group. For this example, we're going to select the US as a reference group. We then might have a regression formula that says y hat, so our predicted life expectancy, is equal to our y-intercept 75 minus 1.5 times if a person is from France, plus 3 if a person is from Japan. So if we want to find the predicted life expectancy for someone born in France, in the above formula, we assign 1 for France, and then for Japan, we give that a value of 0. So this results in the formula y hat is equal to 75 minus 1.5 times 1, because we're talking about someone from France, plus 3 times 0, because we're not interested in anyone born in Japan. This gives us a value of 73.5. So in words, we expect someone born in France to have a life expectancy of 73.5 years. This value of 1.5 corresponds to the slope for France. This indicates to us we expect someone from France to have a life expectancy that is 1.5 years less than someone from the US. Again, because the US is our reference group. We could do the same thing for someone born in Japan as well, except in this case, France would get a 0 and Japan would get a 1. So our formula would be 75 minus 1.5 times 0 plus 3 times 1, or in this case, 72. So we would say someone from Japan has a predicted life expectancy of 72 years. Excuse me, of 78 years. That's a plus. Now, if we want to know the life expectancy from someone born in the U.S., we assign France and Japan as 0. So 1.5 times 0 is 0, 3 times 0 is 0, and we're left with the y-intercept. So that is, we expect someone from the U.S. to have a life expectancy of 75. This tells us that the predicted value for whatever group we designate as the reference group is equal to the y-intercept. Rarely can a single independent variable adequately explain a dependent variable. For example, one's height is not the only variable that affects one's weight. A person's age and diet may play a role too, among other variables. Luckily, regression can be expanded to include multiple predictors. To demonstrate this, let's predict someone's weight using both height and age in years. Let's say this results in the following model. A person's predicted weight, y hat, is equal to our y-intercept of negative 450, plus our slope for height, which is 9, times a person's height, plus our slope for age, which is 0.5, times a person's age. So we have a couple things to point out here. Notice that the y-intercept and the slope for height changed slightly after age was added as a predictor. The interpretation of each of the slopes changes slightly too. The slope for height indicates that for a 1 unit increase in height, we expect weight to change by 9 pounds, when age is held constant. This last statement means that for every possible age in our data set, a 1 inch increase in height is always going to correspond in a weight gain of 9 pounds. So that applies to someone who's 20 years old, and that applies to someone who's 80 years old. We interpret the slope for age similarly. For a 1 unit increase in age, we expect weight to increase by 0.5 pounds when height is held constant. So that means for all values of height, the effective age is a 0.5 or a half pound increase. We can make predictions much like we did before. For instance, we predict a 30-year-old person who is 60 inches tall to weigh negative 450, our y-intercept, plus 9 times 68 inches, plus 0.5 times 30 years of age, or 177 pounds. So let's do an example in Excel. We're going to predict the length of hospital stay using not only age, but also a person's blood pressure. Excel gives us the following results. First, we're going to obtain the regression formula by using that coefficients column in the third table again. Our y-intercept is 14.6. The slope for age is 0.188, and the slope for blood pressure is 0.059. So we want to interpret the effects of age. We say that for a 1 year increase in age, we expect the length of hospital stay to increase by 0.88 days when blood pressure is held constant. Likewise, a 1 unit increase in blood pressure increases the length of stay by 0.059 days when age is held constant. Now, next we need to test whether each of our predictors, independent of one another, predict length of stay. The p-value for age, which we look at the age column and go to p-value, is 6.81 times 10 to the negative 16, which is way less than 0.05. So we reject the null hypothesis and conclude that age is a useful predictor of length of stay. The p-value for blood pressure, which we look at the blood pressure row and find the p-value, is equal to 0.18, which is not less than 0.05. As a result, we cannot say that blood pressure is a useful predictor of length of hospital stay. We can then use the F-test to evaluate whether age and blood pressure together do a good job of predicting length of stay. We go to the ANOVA box, which is the second one, and we look at our F-value of 37.33, and we see a p-value of 2.22 times 10 to the negative 16, which again is less than 0.05. Therefore, we reject the null hypothesis and conclude both of these predictors together do predict length of hospital stay. I want to point out that even though blood pressure alone is not a good predictor of length of stay, when the effect of blood pressure is combined with the effect of age, the overall model does predict length of stay. Finally, how good of a job does our model do of predicting length of stay? We look at our R-squared box in the first box, and we find a value of 6.97%. So we see that our total model only predicts about 7% of the length of stay. So again, although our model does statistically predict the length of hospital stay, it doesn't really do a good job of that prediction. As you can imagine, it's possible to construct an almost infinite set of models to predict a dependent variable. Maybe a model using gender and height is a better predictor of hospital stay than a model that uses age and blood pressure. How do we decide which model is best? Well, we can use the model fit statistics we introduced earlier to pick the best model. The simplest way of picking the best model is to compare the coefficient of determination, R squared, between several models. Models displaying a higher value of R squared do a better job of predicting the dependent variable than models with a lower value. In our first example, we use a single predictor, age, to predict length of hospital stay. That model had an R squared of 6.44%. The second example used both age and blood pressure to predict length of stay. The second model had an R squared of 6.97. Comparing these numbers, we can see that the second model does a slightly better job of predicting hospital stay, since 6.97% is greater than 6.44%. As a result, we would probably prefer the second model. And that brings us to the end of Module 6 and the end of Course 1. I posted a couple documents in MyMethodist to hopefully help you with conducting regression analysis in Excel and interpreting the hypothesis test. Look through those and let me know if you have any questions. Additionally, there should be an evaluation for the course available. It would be very helpful to me if you filled that out. I will be making some changes to the course in terms of making the slides more useful and providing more material. So anything that you think could help the course would be greatly appreciated, I should say. Other than that, good luck with this week's module. Good luck in Course 2, and then you'll see me again in Course 3.